So let's have a look at exercise problem 18.1. Now in this problem we have to show that we can represent this shaded region in the complex plane by a linear matrix inequality of this form 18.6. Note now that in this case we have complex matrices, and we have to show that this complex matrix is negative definite if and only if the complex number s or the complex point s lies in this admissible region shown by the shaded figure. So let's try to do this. We first divide this shaded region. Let's call this region D. We can see that this shaded region D can be written as an intersection of two sets D1 and D2, where D1 is this shaded region and D2 is this slab. We can see that if we take intersection of D1 and D2 we would get the desired D. Now let's find linear matrix inequalities for these two regions separately, because we know that we can just add two constraints to get a bigger linear matrix inequality. So now let's consider the region D1. Now this region D1 can be further decomposed into two regions, D11 and D12. So that is D11 and that would be D12. So note that these angles are still beta. Now we can see graphically that the region D1, which is this one, can be obtained by taking the intersection of the region D11 and D12, and now we will generate linear matrix inequalities for these two regions. So now let's consider this one first. Take a unit vector now perpendicular to this line. We know that if this angle is beta, because this is orthogonal, this would be 90 minus beta and that would be beta. So a unit vector orthogonal to this plane or this line would be cos beta and sin beta. Now so I'm first considering or looking at this region in R2 instead of the complex plane, and we will switch to the complex case later. So T1, if we see this region as a subset of R2, can be written as T11 is the set of all x in R2 such that and let's name this unit vector A1. Such that the dot product of x with A1 is negative definite. So the geometric interpretation of this is that any point or any vector on the other side of d11 would have a positive dot product with a1. The vectors on this line would have exactly 0 dot product because they are orthogonal to a1, and the ones in the region d11 would have a negative dot product. Now similarly we can find a vector orthogonal to this line here, and because again this is beta and this is orthogonal, that would be 90 minus beta and that would be beta. So let's call this unit vector a2, and that would just be cos beta and minus sine beta. Now in a very similar fashion we can write down the set here, that is the set of all x in R2. Note that we are still looking at this as R2 and not as a complex plane yet, as R2, such that the dot product with A2 now is negative. Now once we have this, we know what the dot product means, so that is, let me just write it down explicitly. The dot product just means a11 x1 plus a12 x2 should be negative, and maybe I can also replace a11 because I know that. So what this is saying is that cos beta times x1 plus sine beta times x2 should be non-positive, and here we have cos beta times x1 minus sine beta times x2 should be non-positive. And now we can switch to the interpretation in the form of a complex plane, because we know that x1 is just the real part of S and x2. So now instead of looking at this as R2, we can look at the same region as plotting real part of S versus imaginary part of S, and the same thing here. So because we were treating this as R2, let's call them D11 and D12 bars, because they are not really D11 and D12 because we want the interpretation in the form of a complex plane. So now D11 is the set of all complex numbers such that cos beta times real part of S plus sine beta times imaginary part of S is non-positive, and D12 then is the set of all complex numbers such that cos beta times real part of S plus sine beta times imaginary part of S, minus sine beta times imaginary part of S should be non-positive. Now if we want to take the intersection of these two sets, that's obvious, we just need to impose both conditions, and that gives us D1. So that is D1 1 intersection D12, that is the set of all complex numbers such that cos beta real part of S plus sine beta imaginary part of S is less than or equal to 0, and cos beta real part of S minus sine beta imaginary part of S is less than or equal to 0. Now that correctly characterizes our region D1. Let's note that D1 is still not yet the final region. D1 is this conic region. We will deal with this slab D2 later. So, but we still do not have an LMI yet. So we want to convert these two conditions into a linear matrix inequality. So now in order to do that, let's first look at a matrix M of the form A, IB, minus IB and A, or let me shift the minus sign here. Now the eigenvalues of this matrix can be computed. So the characteristic polynomial would be A minus lambda squared minus IB, so I squared B squared, that is nothing but A minus lambda squared minus B squared equal to 0. So we have A minus lambda minus B times A minus lambda plus B equal to 0. So that gives us the eigenvalues as A plus B and A minus B. Now we also know that M is negative definite if and only if all eigenvalues of M are negative definite. So we can use this to write down the two conditions that A plus B is negative and A minus B is negative if and only if M defined as A minus IB, IB and IB is negative definite, and that's exactly what we want. So if we look at the two conditions here that were characterizing D1, we have A plus B and A minus B. So we can then define now equivalently the set D1 as the set of all complex numbers such that M, which is defined as real part of S times cos beta minus I times imaginary part of S times sin beta, I times imaginary part of S times sin beta, and real part of S times cos beta. If this matrix is negative definite. So that's the characterization of D1. So now we will write down real part of S as S plus S bar by 2 and imaginary part of S as S minus S bar by 2, and then we can obtain D1 as the set of all complex numbers such that beta sine beta minus sine beta cos beta s bar. So half of all of this. Note also that I times imaginary part of s is given by this expression, so we've replaced the real part of s and I times the imaginary part of s in this matrix here to obtain this one, and that should be negative definite, and that's it. So this is then MC, this would be MC transposed, and we would have no LC here. So now we've characterized this set D1 as a linear matrix inequality. Now let's try to do this for the slab D2. Let me quickly draw this once again. So D2 was this infinite slab between alpha L and alpha R. So this one is quite straightforward. We can simply write down D2 is the set of all complex numbers such that the real part of S is between alpha L and alpha R. Again, we know that the real part of S can be written as S plus S bar by 2. We get D2 is nothing but this. And note that we have in fact two conditions here. So one is this one and the other is this one. So if we now write these two down separately, we get D2 is the set of all complex numbers such that, oh, and by the way, we had strict inequalities instead of non-strict ones, so let me change that to strict inequalities. Is the set of all S such that 2 alpha L minus S bar is negative. So that's the first one, and then we have minus 2 alpha R minus a plus S bar is negative, and this can be very easily written down in the form of a linear matrix inequality by just writing down these two conditions along the diagonal to obtain something like this. So that's our LV, that's our MV, and that's our MV transpose. In this case, MV is symmetric. Now we have characterized D1 and D2 by two linear matrix inequalities, but now we still need to build our final D, which was D1 intersection D2, and that can be done simply by just diagonally augmenting the two linear matrix inequalities. So we get D is the set of all complex numbers such that LC was 0, so we only have LV plus and that's it for this problem. Thanks a lot.